system of pulleys and constraint relation in this case of system of pulleys. So today we will look at another additional concept in Newton's laws of motion to do with non-inertial reference frame and pseudo forces. And with that, we will complete the concept set of Newton's laws of motion so that we can now look towards moving towards the next chapter, which will be friction. So anyhow, let's begin. So as I said, we will start with a fresh concept today. Concept of application of Newton's second law in a non-inertial reference frame. So let's understand this term first, what it means. Non-inertial reference frame. And related to that, the concept of pseudo force. So we will start with a couple of definitions. First being the definition of what an inertial frame is. Or simply inertial frame. Or in short, we will just refer to it as IF, inertial frame. So this is a reference frame fixed to the ground. Okay, or moving with uniform velocity. That means it should have zero acceleration. So even if it is moving, it should be moving such that the acceleration is zero with respect to the ground. Okay. And by ground, we mean the surface of the earth. So note down this definition. Now, when we apply Newton's second law in the inertial frame, in an inertial frame, if a body of mass m experiences a net force so this is Newton's second law applied to a body in a inertial frame. So where A is the acceleration of the body with respect to the inertial frame. So this is something that we are used to. This is what we've been doing all along till now. So all the applications we have seen in this chapter till now, we have been using this concept only. Okay, so this is the same as concept used to solve free body diagrams in all situations with respect to inertial frame. So until now, we've been using this equation only. Now we will see a different variation of this, that what if we are conducting our experiment or making a free body diagram with respect to a reference frame which is not an inertial frame. That is, which it does not satisfy the condition that we have written above over here for inertial frame. That is, it is moving with some acceleration. Because the condition for the frame to be inertial is that it should either be at rest or fixed with respect to the ground, or if it is moving, it should move with uniform velocity. It should not have acceleration. So that is the condition for inertial frame. So what if we have a reference frame which does not satisfy this condition? Then how do we deal with the application of Newton's second law? That's what we are coming to in the next part. Okay, so next up, let's understand the definition of a non-inertial frame. Exactly. So that is the correct one. Correct deduction here. That inertial frame is basically that frame in which Newton's first law is written directly in this form, that net force is equal to mass into acceleration. Or Newton's second law can be applied directly as per the definition. Okay, so Ethan, if you finished writing this down. Now let's understand the definition of non-inertial. So it is just kind of the reverse of the definition that we have seen in case of inertial frame. So it is a reference frame which is moving with some non-zero acceleration, or it is having an accelerated motion with respect to the ground frame. So this is a reference frame in accelerated motion with respect to ground, or basically moving with non-zero acceleration with respect to the ground frame. Okay, so now why is this important for us? Let's try to understand. So any body in a non-inertial frame experiences a pseudo force. So the term pseudo is used for imaginary, but here it is used for imaginary because it is a force applied by an imaginary agent. It's not that the force is imaginary. It is the agent who's applying the force is actually the nature of motion of the relative or nature of motion of the non-inertial frame. So it's not really an external agent who's applying the force. So hence it is called a pseudo agent or an imaginary agent. So it experiences a pseudo force opposite to the non-inertial frame's acceleration vector. Okay. And proportionate to its magnitude. So to interpret this statement, let us just think of a couple of simple everyday examples. Now let's say this is some kind of a vehicle which is at rest initially. Now it suddenly it starts. So as it starts, it has a forward acceleration a0. So you see the moment that happens, this person has a tendency to jerk backwards. Right? Experiences a backward force on his body. And if he does not catch hold of something or balance himself, he will tend to fall because of that. So this pseudo force, you will understand, is not applied by some external agent. Nobody is pushing the person inside the vehicle. But as the vehicle accelerates forward, there is some imaginary agent who applies this kind of force on his body backwards. And that is the pseudo force that acts because of the non-inertial phase motion. Similarly, another example is a person is sitting on a vehicle or in a vehicle moving at uniform velocity. So in this case, there is no pseudo force on his or her body. But if the vehicle brakes, That means it decelerates. Then his or her body experiences a force in the forward direction.
So that is the momentum, no?
No, beta. See, momentum is mass into velocity. Okay. He has a tendency to jerk forward because he had a momentum. Okay. But a change in a state of momentum always has to come from force. No? If he was sitting on a chair inside, with respect to the vehicle, what was his momentum? It was 0. Now suddenly the vehicle brakes and he jerks forward. So his body has developed a momentum with respect to the chair. So change in momentum always has to come from force. You understand better?
Yes, sir.
Okay. So who is applying that force? An imaginary agent. But what type of force it is? It is a pseudo force. So whenever you're trying to visualize and understand the concept of pseudo force, you can go back to these two examples and they make things very clear. So if he's sitting on a chair, okay, now the vehicle is moving like this initially, okay, but suddenly it brakes, and particularly if it brakes hard, then his body will experience a forward force, which is the pseudo force. Now, yes, you can say that what is the reason for his tendency to jerk forward? It's partly the fact that he had a momentum and suddenly the vehicle has braked. So because of his momentum, he has a tendency to continue forward. But at the same time, if you look at how his body is responding in the non-inertial frame, that is with respect to the frame of the vehicle. So he did not have momentum initially, he was at rest. But now suddenly he's jerking forward. So he is getting momentum. So something has to generate that momentum. There has to be some kind of a force. So that force that acts, that imaginary agent, external force that acts, that is called the pseudo force. Same for the first example also. As the person gets pushed back like this, okay, again you can say, okay, it's partly because he has inertia, so it's of inertia of rest initially, and as the vehicle accelerates, his body tends to remain at rest because of inertia. So with respect to the vehicle, he ends up jerking backwards. But what if you're looking at the same situation sitting inside the vehicle? So you will not see the vehicle moving. No? In your frame, the vehicle is at rest. So what is causing him to jerk backwards? It has to be some kind of a force. Now there is no external agent applying any force. So that's why this force is called the pseudo force, because the agent applying the force is imaginary or pseudo. Okay. So make a note of this.
What is it written in the left side in the red ink?
Left side in
In the
the
left example. In the left example in the red ink.
example, okay, the object is at rest initially. Okay, now it starts, so it starts motion in the forward direction. Now at t equal to 0, it suddenly starts moving. So as it starts moving, it has to accelerate forward. So the moment it accelerates forward, you will experience the backward force acting on a body inside. Is it clear?
Yes, sir.
Similarly, not just a person, if there's some object kept on the floor like this, even the object will tend to get pushed backwards. So if there's not sufficient friction, then you can see objects sliding back also as the vehicle accelerates forward. Or if the vehicle decelerates because of braking, such objects might slide forwards. So it might seem mysterious how come this is happening, because there's nobody pushing that object from inside. Okay. And in the frame of the vehicle, that object was at rest initially. So how come it started to move? So that mystery is solved by the whole concept of pseudo force, which we'll discuss in the next minute. Okay, just note down these two examples. Okay, so now that we have understood this conceptually, just by visualizing these two everyday life experiences. Yeah, Siddharth, I'm coming to that point. In both examples, it follows inertia of rest or motion, but okay. No, it follows inertia of rest or motion when you are seeing it from ground frame. No, the problem really starts to occur that what if you start analyzing the behavior of the two objects or bodies or whatever in the non-inertial frame? Then how do we, justify this fact? How do we apply Newton's second law, okay, and explain the phenomena from the non-inertial frame point of view? From the ground frame, there's no problem in understanding it. Okay, but the issue is how would we adjust the situation required if our experimental frame, okay, let's say our physics laboratory is such that it is in a non-inertial frame, it is not on the ground, so we are not able to measure anything with respect to ground. We are measuring everything sitting inside a frame which is accelerated like this, like sitting inside that vehicle. Then how do we apply the laws of physics, or in this case the second law? So that is the whole point over here. Okay? So pseudo force, so as we have understood, it is that force applied by a pseudo or imaginary agent on a body inside a non-inertial frame. So it is given by the formula minus m into a naught. But I'm just writing this as a naught to make sure that we understand it is the acceleration of the frame of the non-inertial frame, not the acceleration of the body. Okay? So this left-hand side, this is the pseudo force. Just a minute, people. I have to reshare that file. Yeah. So left hand side of the equation, F pseudo, this is the pseudo force acting on a body of mass m in a non-inertial frame accelerated at this much acceleration with respect to ground. Okay. So any body which is placed inside a reference frame like this, which has an acceleration of a naught with respect to ground, it experiences this kind of pseudo force. Okay. So let's understand that in context of this example now. So if this person is standing at the back of this vehicle, it has a frictionless surface, okay, such that now the vehicle is accelerating at a naught, and the person inside is of mass m, and he's standing on a smooth floor. There's no friction. So if he was standing in the middle of the bus without anything to hold on to, he would definitely slide back. Now what we want to do is, suppose given mass of the person is, let's say 70 kilograms and g is 10 meters per second square. If a naught is equal to 2 meters per second square, calculate the normal contact force, okay, between the person and the back wall, okay, by making his or her free body diagram. So we'll do this with two situations with respect to ground floor. Okay. And this is the normal way that we are used to solving Newton's second law till now. Okay. But now we'll also understand by solving the free body diagram with respect to the bus's frame, which will be a non-inertial. So with this example, we'll understand the application of this concept of pseudo force. Okay. So first write down the definition of pseudo force and then try the first part of this question yourself. Okay. Try to understand that what kind of contact force will be acting between the back of the bus and the person, the back wall of the bus and the person, if I were to make his free body diagram in the ground floor. So suppose an observer standing at rest on the ground is observing this other person and makes the FBD of that person who's inside the bus, then what will this observer say in terms of forces acting on his body and the application of Newton's second law? Then we will see how this can be adjusted for the situation where the observer is not on the ground but is inside the bus and therefore is in the non-inertial frame. The mass of the person is only 70 kg beta, so how can the force be 1 Newton? Anyhow, let's look at this. So we do the first part, we make the FBD of that mass, but with respect to an inertial frame. Okay, so this is with respect to an observer at rest, okay, on the ground. So let's say this is observer A. Okay. So in my diagram above, apart from this vehicle and the person inside, there's also another person who's at rest on the ground outside. and there's observer A, and there's another person who's inside the bus, who's observer B. So when we are looking at the free body diagram of person C, that's okay. So that is this person. So in his frame, what all he will see? So first of all, he will see that person moving with an acceleration of, the person A on the ground observes C to accelerate with respect to his or her frame, which is of course the inertial frame. And in his frame now, what all the forces are acting on the body? There is normal reaction that this wall is applying on him. Okay. Let's say that is N1. There's normal reaction that the floor is applying on him. Let's say that's N2. And there is the weight of the person, mg. So these all forces are acting. So this person will say that N1 is equal to MA or MA not whatever. So N1 will become 140 newtons. This is the normal contact force with the back wall. Okay. And N2 balances mg. So this is the normal reaction that the floor applies. We take GS. This is the floor's normal reaction. Okay, so very simple, nothing surprising in this. Okay, but now we come to the more interesting issue, that what does the observer B see? Okay, for this situation, what does he observe? Because with respect to him, the person C is at rest. Okay. How does he justify that it's at rest when there is these kind of forces acting on it? Okay. So next, when we look at the free body diagram of the person C in the bus's frame, which is a non-inertial frame. So this is our observer B, let's say, who's in the bus. So he is traveling with an acceleration of p naught. So what this he sees is that this object is at rest. In B's frame, that is the non-inertial frame, the object, or in this case, the person, is at rest, is not moving. Okay. But in that person's frame, what is happening is that the acceleration of the frame is generating what we've discussed earlier, a pseudo force. Okay. So you can see that the direction of the pseudo force is opposite to the acceleration, and the magnitude is equal to mass into acceleration. When we write this equation is equal to minus ma naught, what this means is the magnitude of the force is equal to magnitude of mass into acceleration, and direction is opposite to the acceleration vector. That's why you can see the magnitude of this force that I've shown, it is ma naught, but the direction is opposite. Like this. So this actually pushes that person's body against the wall of the bus, and the and that's what's causing the contact force to act. Because see, with respect to that back wall of the bus now, there's no acceleration of the body. So how come it's creating a contact force when you look at it in that frame? Because there's something pushing him against the wall back, and there's no visible external agent doing that. So it's a pseudo force. So this normal reaction is created by this. This normal reaction is created by the weight, and because the body is at rest, so N1 balances the pseudo force. So N1's magnitude is equal to M1, is equal to 140 newtons. Because and N2 on the other hand balances weight. So N2 is equal to mg, it's equal to 700 newtons. Okay, so this is the whole idea, that if we have to apply Newton's second law in a non-inertial frame, so when Newton's second law is to be applied in a non-inertial frame, then pseudo force must be included in the free body diagram. That is the important thing. Okay.
So,
Yes.
so I had a doubt in that with respect to ground.
Yeah, beta, tell Anand.
So, like, there isn't any force that is balancing N1 over there, right? So,
Yeah. So basically
according to that,
N1
it
what?
should the body should be moving inside the bus.
So ground frame में वही हो रहा है ना. See what this person on the ground sees about that other person see. That other person is accelerated ना देखो.
So that is like the bus is being accelerated. The man isn't moving inside the bus, right?
हाँ, but with respect to the person A, doesn't the person C have an acceleration? Because
Yes,
acceleration
sir.
को हम कैसे measure करते हैं? Rate of change of velocity ना. So
Yes,
if
sir.
this person A is observing, C is initially over here, let's say, okay, but after some time C is over here ना. मतलब he can
Yes,
see
sir.
he's moving with the bus, but the fact is with respect to him, he's moving ना.
Yes, sir. Got it, sir.
No, got the point. So see, the
Yes, sir.
measurement is done with respect to the reference frame. Na? So the moment the reference frame is the ground reference frame, your measurement will tell you that, okay, the object C or the object B, whichever, they are having acceleration. Whereas the moment your reference frame is inside the vehicle, so in that reference frame, what is the measurement? That is not having any acceleration, it's at rest. So there is a
Yes.
the mismatch of information between these two. So how do we adjust Newton's laws to take care of this mismatch? So that the answer to that is pseudo force. Now, whenever we get into the non-inertial frame, we have to include the pseudo force.
Yes, sir. Got it, sir.
Okay, very good. Okay, now another very common experience you would have part of our everyday lives. When we step into an elevator, okay, and suppose we are going from a lower floor to a higher floor. So when the motion of the elevator starts, you sometimes feel like for the initial second or two, you're like being pushed towards the ground. You feel heavier. Your body feels like it's a bit heavier. Okay. So why that happens is as you step into the lift and the lift starts moving upwards, it has an upward acceleration. So upward acceleration means your body is getting pushed down with a pseudo force. And similarly, if you do the opposite, you step into a lift which is going to a lower floor. So as the lift starts its motion for a few seconds or at least a bit of time, it has to accelerate downwards. So that time the pseudo force acts in your body in the opposite direction. It acts upwards. So you actually feel lighter. Okay. So these are two common things that happen. Okay, if you observe carefully. Okay. And this becomes even more apparent in like fast accelerated situation. Like if you're in a roller coaster or something, you feel extremely uncomfortable because of pseudo forces acting on your body. Okay, so that feeling of butterflies in your stomach, or that feeling of, even if you take video footage, you'll see that as the roller coaster sort of goes down, your cheeks sort of get crushed like this and all that. So all that happens because of pseudo forces which are acting on your body.
Sir, we jump higher when the lift is going up and suddenly stops. So we jump higher because of the pseudo force only, no?
Yes. So if it's going up and it suddenly stops now, then that means it's decelerating while going up. So the acceleration vector is downwards. So your body will feel pushed upwards. So if that stop happens too suddenly, if it's like suddenly jerks and stops, you can even get lifted above the ground. Okay. So let's understand these examples with some numerical details. Okay. So pseudo forces on a vertically, or rather we can say on a body inside a vertically accelerated reference frame. Vertically accelerated elevator. Let's look at that situation. So now once again, let's say what we have here is there is a block of mass m. There is one person who is inside the elevator. Okay, and there's another person who's observing all this from outside the elevator on the ground. All this is while the elevator is going up with an acceleration. So let's say this is Ayush, who's inside the lift, okay, and is also present with us here. And let us say this is Diti, who is at rest on the ground. Okay. So given the mass of the block is 50 kilograms and E naught is 2 meters per second square, whereas G is 10 meters per second square. So draw the FPD and show forces on the block as seen by Ayush or as seen by Aditi, and calculate the normal reaction force in each case. Okay, so this is the example I was telling you about, that if the lift is vertically accelerated upwards, then an object inside it will seem to be heavier because there's pseudo force acting downwards on it. So it's like, the object feels heavier, whether you're trying to lift it up or whether it's your own body. It's like something adds to the body weight you experience. Okay, so very good. That's correct, Siddharth. Let's look at each of these parts in detail now. So when we look at it from the point of view of Ayush, who's the non-inertial frame inside the elevator. So that frame itself is going up with an acceleration a0. But in that frame, the box or body or whatever, this is at rest. So it's experiencing pseudo force, opposite in direction, ma0 in magnitude. It's experiencing weight, and it's experiencing the normal reaction that the ground is applying. So 600 newtons is a normal reaction measured according to the calculation done by Ayush. Okay. Because he is the non-inertial frame observer. No? So that is why there's pseudo force. He is the observer inside the frame of the lift. So that is which type of observer? That is a non-inertial frame observer. So in non-inertial frame, body will experience pseudo force. Right? Okay. Whereas if we make the second FPD, which is the FPD made by Diti, because she becomes an inertial frame observer because she's at rest on the ground. So in her frame, what is happening? The body will not experience pseudo force, but with respect to her, the body has an acceleration a0 upwards. Something must be pushing it upwards, and that net force is n minus mg. So that is equal to mass into acceleration. So again, that gives us the same result end of the day. But here basically the idea is that n minus mg is the net upward force, which equals to mass into acceleration. Whereas in the above case, what was happening is that when we wrote this statement here, what it basically meant is that normal force balances the sum of weight plus pseudo force. The object is at rest.
Sir, what is the written mass? Mass after that, what do you have written there? In the second one?
Mass into acceleration.
No, sir. That net upward force is equals to mass.
Mass into acceleration. Okay, that is short form for acceleration.
Sir, net force is in the direction opposite to acceleration. Now, for example, our lift is going upward, so pseudo will act downward.
No, don't confuse pseudo with acceleration over here. This is a different thing, beta. This is the acceleration in the ground frame.
No, sir, while talking with the non-inertial frame.
So in the non-inertial frame, the pseudo force's direction is opposite to the acceleration of the frame. फ्रेम का देखो बॉडी का कोई एक्सीलरेशन नहीं है इन द अबव एफपीडी ना इन द नॉन इनर्शियल फ्रेम एफपीडी द बॉडी डज नॉट हैव एनी एक्सीलरेशन द बॉडी इज एट रेस्ट सो द फोर्सेस शुड बैलेंस But along with normal reaction and weight, there is one more force, which is the pseudo force. Now, what is the direction of that pseudo force? That is opposite to the acceleration of the elevator, because that is the non-inertial frame. You are understanding now?
Okay, sir.
So pseudo force will be opposite in direction to the acceleration of the frame. The body is not accelerating in this case. The body is at rest, but the frame has an acceleration of a naught upwards. So pseudo force is downwards. Whereas when we look at it in the ground frame, there's no pseudo force, but the body is accelerating upwards now. So net force should be equal to mass into acceleration, but net force we should take in which direction? In the upward direction, because the acceleration is happening upwards. Okay, now let's start looking at situations which are a little bit more interesting. So just like this example we saw of the elevator with an upward acceleration, all that. Now next we will see that inside our elevator only we have kept a fully mass system. So this time what is happening is our elevator is descending with an acceleration of again 2 meters per second square. G's value is given to us as 10 meters per second square. And the mass of the block A is, let's say, 6 kilograms. And the mass of the block B is 4 kilograms. So we have to find the acceleration of A and B with respect to the elevator's frame, and again with respect to ground frame, and also the tension in the thread. So this is a standard pulley system. Okay, so the pulley is a smooth fixed pulley and the thread is massless and inextensible, all those assumptions you take. But only now the system is not, the pulley is not fixed to a fixed ceiling, rather is fixed to the ceiling of an elevator, which is accelerating downwards at 2 meters per second square. So you have to find what acceleration you will observe for the blocks A and B. If you were sitting inside the elevator, so in that frame, what is the acceleration you would observe? Or consequently, if you are outside the elevator at rest on the ground, then what kind of acceleration you would observe? Both the things we have to calculate. So just try this out, people. So here, one thing you understand straight away is that the motion of the blocks is much easier to understand if we are observing from inside the pulley, sorry, inside the elevator. Inside the elevator's frame, what we will see is that it's a very simple type of situation. The blocks are like this at time t equal to 0. This is going down and this is going up. But this is, the pulley remains where it is. So after some time, so A's downward acceleration is equal to B's upward acceleration. Why? Because the pulley P is at rest. But the same thing if you observe from the ground frame, is much more complex. Because what is happening in the ground frame is the whole system is descending. So the pulley is not at rest. This is at t equal to 0. So after some time, at t equal to t, the pulley itself has come down along with the elevator. So the pulley is here now. This has become much more complex. The pulley has a downward acceleration. The block A has a downward acceleration. The block B has an upward acceleration. So it is more complicated. So we won't use this. We'll use this because this is easier. But if we are using the first diagram, that means we have to apply Newton's law in the elevator's frame, which is a non-inertial frame. Okay. So A and B's motion are easier to analyze in the elevator's frame rather than the ground frame. It's not easy in the ground frame. It's more complicated. But to observe in elevator's frame, we have to make FPDs in the non-inertial frame. So pseudo force has to be included. Okay, so people, hope you understood this point over here. Okay, first of all, that how we have decided this thing, that how to go ahead with Newton's laws over here to choose the elevator's frame as the convenient frame, not the ground frame, because in the elevator's frame, the pulley is stationary. Okay, so it's going to make life more simple. In the ground frame, the pulley itself is accelerated. So it's not going to be that easy. Okay. So now once we have decided that, let's understand the free body diagrams in detail.
Sir, can you explain again the previous one that you just did?
Yeah, this diagram will make it clear. The one I'm making now. So if we are observing this system from inside the elevator, okay, so then for us, what is happening? The pulley is at rest in this frame, okay, in the elevator's frame. Okay. The pulley is at rest, which means that whatever downward displacement the block A will have, the block B will have an equal and opposite upward displacement because the pulley is at rest. So with respect to the pulley, they should move by the same distances. You're understanding the point now? This acceleration and this acceleration will be same because the pulley is at rest. Okay. So here A is with respect to the elevator's frame. And that frame itself is doing what? It is accelerating downwards at T0. Okay. So in the elevator's frame, let's make the free body diagrams. So this frame is accelerating downwards at T0. So whether we are making A's free body diagram or we are making B's free body diagram, both of them will experience pseudo force. Both of them will experience pseudo force in the downward direction because the acceleration of the frame is upwards.
Sir, pseudo force will be in upward direction, no?
It has pseudo forces. Oh, sorry. Yeah. In this case, correct. My mistake. The lift is not accelerating upwards. The lift is accelerating downwards. Okay. So pseudo force should be opposite that. That's correct. Okay. So these two are the pseudo forces. Acting on each of them. Now they have their own weights acting. And there is tension acting on each of them. But because A is the heavier block, so A will end up accelerating downwards, B will end up accelerating upwards. And remember that this acceleration is in the non-inertial frame. So it is the acceleration that the observer inside the elevator is seeing for both the blocks. It's not the acceleration that the ground frame observer is seeing. Okay. So now let's write the equation for each one of them. So for A, the net force should be downwards. So weight is dominating over the sum of tension and pseudo force. And that is providing A with an acceleration like this. So this will become now mass of A, I think we're taken as 6 and 4 kgs and A0 was 2. So let's use that. So 60 minus P minus 12 is equal to 6E, or 48 minus T is equal to 6A. That's our first equation. And similarly, let's write the FBD equation for block B. So for block B, tension plus pseudo force acting upwards is dominating over weight to give it an upward acceleration of T. So T plus 4 into 2, 8, okay, minus 40 is equal to 4A. So T minus 32 is equal to 4A. This becomes the second equation. So now equation 1 and 2 can be added. So we get rid of tension. So 48 minus 32 is 6 plus 4E. So you can see that the acceleration becomes
1.6.
1.6 meters per second square. But this is the acceleration of, so A has an acceleration of 1.6 meters per second square downwards. B has an acceleration of 1.6 meters per second square upwards with respect to the elevator, or in the elevator's frame, not in the ground frame. I'll come back to what's happening in the ground frame. Okay. Also, I'll write these equations parametrically instead of this. If we write this parametrically, we have ma into g minus a naught minus t is equal to mass into acceleration, and we have t minus so now if we add these two equations, you can see that we get ma minus mb into g minus a naught is equal to ma plus mb into this acceleration. Which if you substitute, you can see you get .2 into 8 or 1.6 meters per second square. Okay, so this is the same thing, but I've just solved the equation parametrically first, and then substituted the values. This is the same as this. Okay, so just note this down and make sure you understand the free body diagrams, the direction of pseudo force, and the equations that we written very carefully first. So as you analyze this couple of times, you'll just realize it's like any regular pulley system, pulley mass system, but it's just like because of the pseudo force, it's like the effective weight of each block is becoming lesser. It's becoming m into g minus a. Just like in a lift going upwards, the effective weight becomes more. It becomes m into g plus acceleration of the lift. Here in a lift coming downwards, the effective weight of each body becomes m into g minus a naught. Ayan, actually pseudo force more than a reaction force. Now it is a force that acts because of the acceleration of the frame. Okay, it acts because of relative acceleration or because of relative motion. So the reason why pseudo force acts is to do with the acceleration of the frame and the inertia of the body, both things put together. These two properties, the acceleration, the motion of the frame and the inertia of the body, these two together are responsible for the action of pseudo force. So that's why you can see that the formula of pseudo force has both the things. It has the mass of the body, which is basically a measurement of its inertia, and it has the acceleration of the frame. Okay, Siddharth, I'll just verify your answer. Seems correct. Okay. If we just substitute the value of A in any of the two equations, then we'll get the tension. So, for example, it is 32 plus 4A, and okay, so 32 plus 6.4. Yes, yeah, so it's correct.
Sir, we have to find the tension also, no?
Yeah, yeah. So that's what I was saying. Just substitute A in equation 1 or 2 above and you'll get the tension, whichever one you want to substitute. So for example, it is 48 minus 6A, or it is same thing as 32 plus 4A. Yes, and that is correct.
Sir, we have to solve these types of problem using any one of the reference frame, no?
Yeah, in general, you have to solve using one of the reference frames. But the thing is that, you know, it is a matter of your practice that it will teach you that in which type of problem, which reference frame you should take. Like I will show you that in this question, if we had taken the non-inertial, sorry, the ground frame, then the solution would be more complicated. It's much easier to solve it in the non-inertial frame. So like that, as we see more complicated questions, we will see that sometimes we come across a question where we really cannot solve it in inertial frame. We have to solve it in non-inertial frame. So in that case, we don't have a choice.
So,
Yes.
sir, could you please explain that how did you find those equations?
Okay, so the equations are from net force is equal to mass into acceleration. So the block is accelerating downwards. No? So what is the net force in the downward direction? It is the vector sum of the three forces I've shown you. So mg is acting downwards, whereas pseudo force and tension are acting upwards. No? So it is mg minus that sum of tension and pseudo force. So that is equal to mass into acceleration. Have you understood this now? It's like this: if body is accelerating downwards and there are three forces acting on it, F1, F2 and F3, then when we write net force is equal to mass into acceleration, here the net force's direction should be taken with downwards. No?
Yes, sir.
No, so it should be like this. So F1 minus the sum of F2 plus F3. So this is what we have applied to the block E. And the block B, the direction is just reverse. So we should take the force in the upward direction as positive and downward direction as negative.
So then we should take the acceleration of that whole elevator into consideration only while we are looking for the pseudo force, right?
Yes. See, what is happening now? As an observer, we are inside the elevator. So we are not seeing that acceleration A naught at all. No? So it's not taken in consideration as an acceleration. With respect to us, the elevator is at rest, the pulley is at rest, that's why. Okay. But
Yes.
because we are in a non-inertial frame, so any body in that frame will experience pseudo force. So that's why the pseudo force is present.
Okay, sir, got it, sir.
Whereas if we are solving in ground frame, we will see it's the opposite of that. We will have to take the acceleration of the elevator into account for the motion. But then we are in the ground frame, so there is no pseudo force acting on the body.
Yes, sir.
Okay. Ethan, the value of tension is not correct actually. I'll show you the answers for the second part also. Okay, so anyway, now substitute this back in this equation or this equation, whichever, and we'll get the tension as
38.4 Newton.
0.4. Yes, that is correct. See, that pseudo force will also act on the hinges of the pulley. But generally, we take the pulley to be very light. So if we have a massless object, then pseudo force on it is also tending to zero because m is tending to zero. So we need not worry about. But yes, if we are considering a heavy pulley, okay, or something like that, then if we make the FBD of the pulley, we'll also have to consider the pseudo force acting on it in the non-inertial frame. Okay, so now what we can also see is that from this we can also say that therefore with respect to ground, what is happening? A has a downward acceleration of how much? A naught plus A, because it's inside a reference frame that is coming down at A naught, and in that frame it's moving at 1.6 downwards. So it has a net acceleration of 3.6 meters per second square downwards. Whereas B has an upward acceleration of A minus A naught. So that will actually come out to be a negative acceleration. So that means B is actually coming down with an acceleration of 0.4 meters per second square. So with respect to ground, this is what is happening to A. And this is what is happening to B.
So tension is still the same, right?
Yeah. Yes, Ethan, tell me what is your doubt, better. So tension I have found from the equations in the non-inertial frame only. No? We can do it from both actually. It will give us the same value of tension. But what is easier, which I have shown you above, is the free body diagrams in the non-inertial frame. Now next I'll also show you how to solve this problem from the inertial frame point of view. But you will see that it's more complicated in comparison. It's better to use these equations which I've got. Okay, so let's move on to
Sir,
the ground frame.
sir,
Yes.
sir, how come B and A both with the reference to the ground both come down?
Because the
One
pulley
has
is
to
coming
go
down
up.
at a very fast rate, better. That's why it's happening. The pulley itself is coming down at 2, na? You understanding, na?
Yes, sir.
It's like, if you are, let's say, walking inside a bus in the backward direction at 1 meter per second, but the bus during that time is actually moving at 5 meters per second. So in ground frame, what is happening? You're still moving away, na? You're moving with 4 meters per second away on the positive side, na?
Yes,
So
sir.
something like that is happening over here. Okay.
Okay, sir.
Okay, so let's see how we can demonstrate this from the ground frame point of view, though it's more complicated. So our ground frame observer, so solving the free body diagrams with respect to ground. So in that frame, what is happening is, suppose I assume that, so the elevator is coming down at A0. So I'll see the pulley coming down at A0. Okay. And let me assume I see this one coming at A like this and this one going up at AB like this. Okay. Because I don't know right now whether it's actually going up or going down, the block B. So I'm just making a guess or an assumption that is going up. But later I'll show that AB is negative, which means that it's actually coming down. So with respect to the inertial frame, the pulley, it has a downward acceleration of A0. Okay. The block A has a downward acceleration of this much, and the block B has an upward acceleration of EB. Okay. So now because the thread length is constant, you can see A0 minus, sorry, AA minus A0 should be equal to on the other side A0 plus EB. This is like a constraint relation. Do you agree with this? How this is coming? It's coming from the thread length concept. The thread length is constant. No? So after some time, if the pulley has come down, this block has gone up and this block has come down, then the total thread length should remain conserved. So if this displacement is SA, this displacement is SP, and this displacement is SB, then this side the thread length is increasing by SA minus SP. That side it is decreasing by like this one. So when you double differentiate this, you get is equal. So this is what is more complicated in this method. And this can be avoided completely by moving into the frame where the pulley is at rest. So this is a thread link concept. Now in this frame, there's no pseudo force. There's only tension and weights. Okay. So in this inertial ground frame, if I make the free body diagrams of A and B, so I'll consider only tension and weight. Additionally, I'll have the equation. So this one I can write like this, that now here so from equation 1, I have and from 2, now substitute this 2 in equation 3. So we have one by 6 plus 1 by 4. That's how much? 10 by 24. So this will give you the same result. But as you can see that this is just we have done to prove the point that we are ultimately going to get the same result that we would have got by the non-inertial frame method. But this is not very easy thing to do. Okay? This is much more complicated and lengthy. So therefore, preferable for us here would have been to solve it by the first method that I've shown above, that you make the free body diagrams in the non-inertial frame and find the acceleration with respect to that frame. And then you can always go back and find the acceleration in the ground frame by using the acceleration of the elevator with respect to ground and superimposing that. Okay, Siddharth. So that is the whole idea, no? Because acceleration is a measurement of rate of change of velocity with respect to time. So it's a measurement of motion. So obviously, if we are measuring something from a moving frame with respect to measuring with in a ground frame, we are going to get different values. No? Yes. So Sanvi, I will be sending a worksheet also, but first of all, you have to complete all questions from H.C. Verma of Newton's laws of motion chapter. There are quite a few questions which are based on pseudo force and the application of non-inertial free body diagrams. So this week, before the next lecture you have to make sure that you attempt each and every question from H.C. Verma, because we are going to be discussing doubts and questions specifically from H.C. Verma also in the next lecture.
Yes, sir.
So that's part of your homework, okay?
Yes, sir.
So do we have to leave after we have copied?
Yes. So that's it for today's session. If you've finished writing this down, you can complete the lecture. Okay. So make sure to revise this concept of pseudo force carefully, read it from your reference books also, and most importantly, attempt questions from H.C. Verma. Now you should be in a position to attempt each and every question in the Newton's laws of motion chapter. I think there are 52 odd questions or something like that. So please work hard on this over the next few days. And in the next session that we have, we will also discuss specific questions and doubts from H.C. Verma, apart from more practice with pseudo forces. Okay. So with this, we are done with the concept set of Newton's laws of motion. We will keep one lecture aside for questions and doubts, and then next lecture after that, we'll move on to friction. So that's it for today's session, people. Wish you all the best and have a nice day.
Thank you
Sir, I
so
have a
much.
doubt.